So quiz will be posted in Canvas, and it will be it will be published after the session. Yes, sir. It's over to you.
So good afternoon, sir.
Good afternoon, sir. So you can continue.
Is it audible?
Yes, sir. Audible.
Okay. Okay. Yeah. Thank you. Thank you. Yeah. So good afternoon to all. Yeah. So today we will see the topic reversible computing, universal quantum logic gate and circuits. Okay. So why it is relevant to the quantum computer? So everything we will just discuss. Okay. So today's lecture objective will be understanding the concept of reversible computing and identifying and analyzing basic reversible logic gates, understanding foundations of quantum logic gates, recognizing universal gates in quantum computing, and building and interpreting small quantum circuits like half adder and full adder. Okay. And so just to appreciate the application and significance of this reversible gates in the future computing. Okay. So first of all, yeah. So global energy budget. Okay. So now nobody is without laptop, nobody is without desktop, nobody is without mobiles. Okay. Oh, screen sharing. Okay, okay. Yeah, sorry for that. So is my screen visible? Is my screen visible? Okay, okay, thanks. So today we will see reversible computing, universal quantum logic and circuits. Okay. So we will understand what is reversible computing and why it is needed. Okay. And how to construct the reversible logic gates, and then how it is relevant in the quantum computing also, and how to build a simple circuits with reversible logic gates. Okay. Okay. So today's scenario, we are using, everybody is using electronics. So computers, laptop, desktop, monitor, mobile phone, everything. So the total energy consumption of this is very high actually. And it is the size of the electronics also getting smaller day by day. Okay. So I think everybody knows about the Moore's law and other things. So now everything is failing. Okay. For every 18 months, the number of transistors in the chip will get double. So those things are actually now the most of the laws, Moore's law and other things are failing because of quantum effect. When the size become smaller and smaller, that it does not obey the rule. So the electron passes through the barriers. Okay. So server and data center, it is total is around 1.5 to 2.5% of the global electricity. Okay. So as of 2023, so we are using around 1000 gigawatt per hour. Okay. So energy is a major concern. Okay. So there was a thought experiment. So we should brush up the second law of thermodynamics. So second law of thermodynamics states that the entropy in the closed system will never decrease. It will always increase. Okay. So that was the second law of thermodynamics. But James Clerk Maxwell in 1867, he just proposed some thought experiment to disprove that second law of thermodynamics will not work if it is in the microscopic scale. So what he is deciding, what he's telling is, so he's telling that okay, there is a demand. So here this entropy is more. So disorderness is more. So here the order is, so these blue things are the cold atoms and the red balls are the hot atoms. Okay. So when it is not ordered, okay, the entropy is high. Okay. So disorderness is more. So in the closed system, the entropy will always be high. That was the second law. But he is proposing, okay, in case if there is a demon sitting here and it is opening the valve of the gate, okay, by trapdoor, by considering the speed of the atom. Okay, if the more speed, then that may be hotter atom, the less speed, that may be the colder atom. So it is opening the door for some cold or hot atom, and eventually one by one it enters to the other wall, and for cold atom, if it is opening, then it is not opening for the hot atom. That means over time period, some cold atom and hot atom will be separated. It will be in the different chambers, so that some orderness is created. That means the entropy is decreasing. So he's trying to disprove the second law of thermodynamics. Second law of thermodynamics states that in closed system entropy will never decrease. Okay, but he want to disprove it. Okay, in a closed system, so this so demon is opening the door and closing the door, so it is creating order in the system, that is entropy is getting decreased. So he want to disprove second law of thermodynamics. So it was proposed in 1867. Okay, so here a demon settings here. So demon sorts gas molecule like a trapped door based on the speed. Okay, one side become hotter than the other side seamlessly violates the second law, which forbids decreasing in entropy in an isolated system. By converting information about the position and velocity of each particle into energy, the demon is therefore able to decrease the entropy of the system without performing any work. So this demon is, with the knowledge of which is cold atom, which is hot atom, it is just opening or not opening the door. So with that knowledge only, without doing any work, it is able to create order in the system. If there is an order in the system, then there is a less entropy. So it is contradicted to the second law of thermodynamics. So he proposed this in 1867. After that, nobody is able to disprove this Maxwell demon theory. Okay, after 97 years, okay, this Landauer principle came. So he disproved this Maxwell's demon, and he proved that second law of thermodynamics is valid. So he is telling that information is physical, not logical, as proposed by Maxwell. Okay, information is physical. So thermodynamics cost is there for every erasing of the memory. Okay, so erasing information has a thermodynamical cost. So the demon must store information. So what he is telling is this demon might be having the information of which is hot atom, which is cold atom, and then for the next atom it is erasing those informations, and again after sorting out, again it is erasing that n minus 1, then again it is going to n. So it is erasing the information. This erasing the information costs some energy. The erasing information has a thermodynamic cost, so the demon must store information, which particle are faster or slower, and eventually erase it to continuous operation. So any logical irreversible manipulation of information, such as erasing of a bit. So if you are erasing, then you cannot bring back it. So that is irreversible operation. Erasing a bit is a irreversible operation. So whatever the irreversible operation you do, so there is a cost, energy, thermodynamic cost is involved. Okay, must be accumulated. So that he is telling that energy is kBt logarithm of 2. Okay, kb is the Boltzmann constant, T is the temperature in Kelvin, room temperature in Kelvin, and logarithm of 2. That equals to 0.018 electron volt, okay, or 2.9 into 10 power minus 21 joules heat. So for every bit erasing, you are going to spend this much energy. So the demon is erasing this information. This demon is erasing this information for every atom. That means this much energy is spent. So he is disproving that without doing any work, the entropy cannot be decreased. So that was the second law of thermodynamics. So Maxwell's thought experiment was disproved by Landauer's principle, and then he proved it through experiments also. So these are some of the milestones of experiments. In 1961, he proposed this principle, refining von Neumann's earlier conjunction, and then 2008 to 9, okay, he linked it to the second law of thermodynamics, connecting information erasure to entropy and the feedback control mechanisms. And then in 2011, generalization entropy increases from erasing, need not cost energy. So entropy increase from eraser. That means if you are erasing the information, then the orderness is reducing. If orderness is reducing, then entropy is increasing. Okay. So information, entropy, and energy has relationship. We will deal that in the next slide. Okay. So first experiment was direct experiment, bit erasure. So it's published in Nature article, and several physical experiments validating Landauer's prediction was proposed, and laser probe. So many experiments confirmed he is correct. Okay. So through optical traps, nanomagnets, quantum spins. Okay, with this all these methods they used this experiment, and they proved that for any eraser of energy, eraser of information, so you have to lose the energy, and that energy will be lost as a heat. Okay. So entropy is orderness. Okay. Disorderness or uncertainty in the physical system. If entropy is more, then disorderness is more. Okay. Information, a measure of reduction in uncertainty where we observe or measure a system. So more entropy means less information we have, less entropy means we have more information. So how entropy and energy is linked? When entropy increases, the system absorbs or loss usable energy. Okay, when there is no order, then energy will be wasted. Okay, so entropy is a measure of how much energy is no longer available to do work. So if a system has more entropy means less information, then more energy will be wasted. If the information is less, entropy is more, and the energy waste. Okay. Okay. So now, so why reversible computing? So whatever the conventional computer we are using, those are irreversible computer. Okay, that means these computers are made up of gates, logical gates, AND gate, OR gate, NOT gate. Okay, NAND gate, NOR gate. So these gates actually they do not have one-to-one mapping between the input and the output. For example, AND gate, they have two inputs and output is one. So physically, if you see, two input will get some, for example, zero point 0.5 voltage or plus 5 voltage. Okay. And that means two input, that means 2 into plus 5 voltage, that is around plus 10 voltage it is getting, but the output is zero point 0.5 voltage only, plus 5 voltage only. So that voltage 10 voltage is given as an input, and in output you are getting 5 voltage only. That means the remaining 5 is lost. How it is lost? It is lost as a heat. So that's why our present day irreversible computer, whatever we are using, that is the irreversible computer, they use more energy. So most of the energy is not useful actually. It is wasted as a heat. So they thought, okay, then actually, so based on this, his principle, this Landauer principle, another IBM scientist, Charles H. Bennett, he proposed, okay, IBM fellow showed that energy dissipation problem can be avoided if the circuit are built using reversible logic gate. If you build a circuit with reversible logic gates, then this heating energy that unnecessary it is going waste, that energy we can conserve. Okay, and the computer will take very less electricity. So AND gate, two input and one output, so its information is lost here. Okay, in Toffoli gate, input and output information preserved. So total number of input and output is same in reversible computing. Okay, reversible gates, so that the heat and the energy waste will be removed from here, so that total and overall it will take less energy. Okay, it should contains an equal number of input and output. Each input should map to the unique output. Erasing one bit of information, this is the actual thing. Erasing one bit of information dissipates at least kt logarithm of 2 joules of heat, that is approximately 2.87. Excuse me. Yeah, dissipate at least kt logarithm of 2 joules of heat. Okay, 2.85 into 10 power minus 21 joules at room temperature. So K is the Boltzmann constant. T is temperature of room temperature at room temperature in Kelvin, and logarithm of 2. Okay. So any doubt? Okay. How entropy and energy are interlinked and correlated to each other. Okay. See, entropy is disorderness. Okay. If there is a disorderness, then information is less. If you have more information, then disorderness will be less. Okay, and if you have less information and disorderness more, then automatically the energy, for example here you see, yeah, information is an energy cost. Storing, erasing or processing information physically consumes energy and increase entropy. So if you are consuming energy, okay, then that means consuming energy means you are erasing information. If you are erasing information, entropy will increase. If entropy increase, energy will increase. Oh, sorry. Okay, I will slow down. How entropy and energy is linked? Correlated to is that? Okay. If information increases, if you have more information, I can say some analogy. If you know more about your wife, okay, that is information. Okay, so disorderness will be less. That is entropy will be less, and that wastage of energy will be less. So that is how information, entropy, and energy is linked. More information is less entropy, and less waste of energy. Yeah. So I always erasing and not reading and writing a bit. Okay. No, reading, writing, that actually in storage point of view it may be okay, but in processing, for example, you are giving two input for the AND gate, okay, A and B, but the output is C, so output is single output, okay. You cannot reverse it. That means that input is lost. After generating the output, that input is completely lost. That is loss of information. That means the input is already stored somewhere in register, okay, somewhere in the flip flops or somewhere in the register. That means you are erasing it for reusing that register, okay. You are move instruction, that assembly language move instructions, that means you are reusing that register by storing the new value. That means you are erasing the old value. That's why always the erasing, always it takes the energy, okay, it takes the energy in the form of heat. Definitely heat energy we don't need, actually it is waste. Why we need our laptop to generate heat? That energy we are not going to use, okay. So every operation we are erasing it, okay. That input, whatever we are giving input to the gate, that is being erased. So erasing means information lost. Erasing means information lost. Information lost means entropy increasing. Entropy increasing means energy waste increasing. That energy waste is comes as heat, okay. Entropy and energy are linked. As the energy disperse increase, entropy shows more disorder in the system, okay. Yeah, and not energy increase, energy waste increase actually. It's energy waste increasing actually, because that energy is not doing any useful work. That heat energy is not going to do any useful work. That heat is happening because of irreversibility. Yeah, yeah. So irreversible and reversible logic gates. So this is the logic gates and the gate, okay. It has two input and one output. So physically how we will give some input voltage to this. So usually computer takes plus 3 minus 3 plus 5 minus 5 plus 12 minus 12. These are some of the set of voltage which we give for the computer, okay. So we are giving power to the computer. There is a smps. Smps converts the power into the required voltages, okay. Plus 5 minus 5 plus 3 minus 3 plus 12 minus 12. So basically we are giving some voltage, okay. So that means we are giving two times voltage and current, but we are getting one time only. That means half of the current is wasted here. That waste current is coming out as a heat. So if the number of inputs and number of output is not one to one mapped, then definitely you are going to lose the information. Then obviously that energy loss will be there. But in reversible logic, the number of inputs and number of output will be same, okay. That we will see. We will explain everything in next slides. The fully gate and all we will explain next, no issue, okay. So okay, so can you say that information is a measure of entropy? Yes, information can be measured as a entropy or as a energy. So all three has a relationship. Yes, entropy is a measure of randomness, not disorderness. We cannot say randomness, but disorderness. Yeah. External factor disturbance. No, this is we are dealing with see actually, okay. So right now we are using classical irreversible computer, okay. Whatever this laptop or whatever I am using, mobile phone, everything is a classical irreversible computer, okay. Now we have, now if we convert this classical irreversible gates to reversible gates and implement the same logic, then it become classical reversible computer, okay. Quantum is different. Quantum is different. So in quantum only the external factors, and but here it is electronics only. The reversible computer, classical reversible computer is electronics only. Quantum also follows reversible gates. Quantum also consider reversibility. Quantum also has the reversibility property. So basically we have three computers, we can say. One is now at present we have classical irreversible computer. Maybe in future all this AND gate OR gate, all these logic gates can be implemented in the reversible logic. Okay, and then with that components computer can be built. That computer can be called as classical reversible computer. And quantum computer is, it's not classical. Okay, so in quantum computer computation, that gates are reversible gates only. Okay, in quantum computer also the gates are reversible gates. Okay, and the measurement is irreversible in quantum. But in classical reversible computer, if you just redesign the entire circuits with reversible gates, it become reversible computer. That is classical only. Again, it is classical only. Okay. Yeah. This disorderliness loss of information, sir. Yes, disorderliness is loss of information. Or reversible, we can say. Information losses, it will create a disorderness. If you know more inform, if you are aware of, if ignorance is the cause for every problem, that means ignorance is nothing but information loss. So for all problem, disorderness in society, everything, that information loss is the problem. If you have more information about a person or anything, that orderness will come automatically. Loss of information is the creation of disorderness. Shannon information theory also, it's entropy. Actually, I am not into physics department, but it's almost similar only. Thermodynamics, entropy. There are a lot of entropies are there. Yeah, Shannon information coding. He is the first person to propose this. So entropy is disorderless information, and these are all related. It's thermodynamic also related actually. I think there won't be any external factor disturbance, because in quantum only this external factor disturbance, these things are coming in. But here, I think there is no external factor. As per my understanding, I think there is no external factor. Yes, two inputs are erased after C. So that's why we cannot take it back. From C, we cannot produce A and B. I think energy and information related. I think now everybody understood. I think energy, information, entropy. See, external factor may be ambient temperature also, because yeah, ambient temperature may be the external factor. If we consider, if you want to consider some external factor, ambient temperature can be considered. Yeah. Okay. In normal PC, while working with the MS Word, if we delete a line or paragraph, the bytes are increased. Why? I never noticed it, but definitely it should decrease actually. Maybe how they are allocating the, because while creating the file only, maybe they are allocating some minimum memory or something, maybe like that. Can entropy reduce in a system be directly converted into usable work without increasing entropy elsewhere under account of the product? Can entropy reduces in a system? Yeah, that's what people are trying. So that's what people are trying. So they don't want to waste the energy, they want to loop it so that it will be circulated inside the chip only, and some useful work can be done. So that was the logic actually in reversible computing. Yeah. If measurement is also a quantum state, why it is not reversible? Yeah, measurement is not reversible. Once you measure in quantum, yeah, in quantum only we are going to measure, but in classical reversible computer there is no question of measurement. Okay, but in quantum computation is reversible, but measurement is not reversible. Once you measure, the quantum state collapses. Yeah. Yeah, information is a measure of randomness. Yeah, More randomness, less information. More information, randomness will be less. Yeah. Sharing. Okay, share. It's already in shared. Yeah, so maybe this is the reason. Yeah, because it's directly it has buffers. Yeah, many mechanisms comes into that. Yeah. Okay, we'll continue. So I think until this, everything is okay. So Maxwell thought experiment was it want to disprove second law of thermodynamics. Okay, but after 97 years, Landauer principle told that information is not logical; it is physical. So every erase we have to give thermodynamic cost. Okay, then it is experimentally proved. Okay, yeah. So K is the Boltzmann constant, T is the temperature in Kelvin, room temperature, logarithm. So these things. Okay. So in reversible computing, every time you erase one bit of data, okay, a flip of memory cell from 1 to 0, you may release at least this much heat. Well, this is a tiny amount. Modern CPU can process billions of bits per second, and this adds up to a significant heat. In reversible computation, since no bit is erased, okay, KT logarithm of n dissipates can theoretically be avoided. Okay, why entropy matter in future computing? So reversible computing, that is classical reversible computing, also future computing, quantum computing, also future computing. Okay, so entropy is irretrievable loss of information. As we push towards smaller, faster, and denser computing system, thermodynamics limits matter. Okay, so now we are in 3 nanometer scale processors. Okay, to build ultra efficient system, even quantum computer, we must have preserve information, that is reduce entropy increase. Okay, so irreversible computing, erasing information, entropy increasing, heat generated. In reversible computing, no information is erased. That means entropy is constant. In quantum computing, gates are reversible, but measurement is irreversible. Energy efficient computing require minimum entropy production. Okay. Okay. So let's say we have just 2 plus 2 is 4, for example. So 4 we are given and we are asked to find the input. So input can be 2 plus 2 or 1 plus 3 or 0 plus 4 or 5 minus 1. But you cannot actually predict what is the original input. That is irreversibility. Okay. So most of our logic gates, AND gate, OR gate, NAND gate are irreversible. Okay. You cannot generate the input from the output. Okay. To make it reversible, okay, let's consider. So instead of doing only addition, you just do the subtraction also. Okay. So, so here, if you do just x plus y in this output, see here you notice this number of input is 2, number of output is 2. For any reversible thing, output and input, number of input and number of output should be same. Okay, one to one mapping should be there. Okay, so x plus y is given here and x minus y is given here. So by having the output, that is x plus y value and x minus y value, here x plus y is 8, x minus y is 2, then easily you can find out x and y. Okay, then it become reversible. Okay, so x, then oh sorry, y minus 2x is equal to 10, x equal to 10 by 2, it is 5. So similarly y, so 8 is equal to 5 plus 3, 5 plus y, so y is equal to 8 minus 5, y is equal to 3. Okay, so this is reversible. Okay, to make any operation reversible, the number of input and number of output should be same. So why computer use energy? Because we have implemented computer with irreversible logic gates. That's why it is using energy. Otherwise, it will use near zero energy. There is one company in US. They are starting reversible logic gates, and they are producing computer with that. They are naming it near zero energy consumption. So very less energy, because 80% of the energy goes as a heat because of this irreversibility. Okay, so that's why computer use more energy. Otherwise, computer will be using very less energy. Okay, so classical computer is inherently irreversible. Bits are lost in and are not, leading to information erasure. Erasing information consume energy. As per Landauer, erasing one bit dissipates at least kT log 2 joules of heat. Okay. K is a Boltzmann constant. T is temperature, room temperature in Kelvin. That is 300 Kelvin. Heat generation leads to power inefficiency. Okay. So again, heat. If more heat is generated, that heat also create a problem for the circuits, like throttling. Okay, CPU throttling. So all other side effects also comes because of that heat dissipation. Miniaturing versus the issue. Okay, so transistor size decreasing up to 2 nanometer now. So this also leakage current, thermal limit become critical. Okay, emitter base collector, that base, the barrier is not stopping, quantum effect starting. Okay, all these issues. Okay, how to make a reversible computer. Okay, so we have irreversible computer now. How it is implemented? Physical implementation is there. Okay, through transistors. Then gate level implementation is there, and gate, or gate, NAND gate, NOR gate, universal gates. Okay, then computer architecture comes, then machine code, then high level language, then algorithm we are using. Okay, so this is the way we are building the irreversible computer. Same way we have to build the reversible computer also, but everything is different here. Physical implementation completely different from the existing one. Gate level implementation also different type of gate has to be formed, and architecture has to change, machine code has to change, high level language has to change, algorithms also probably may change. Okay, so AI's exponential growth is driving demand for more powerful chip architecture. Okay, so because of artificial intelligence, machine learning, these developments, okay, now we need more powerful processors. Otherwise, earlier our processors are okay for our serial applications. Okay, now parallel application, artificial intelligence, many data crunching, lot of parallel operations. That's why we are going for GPUs. From CPU we are going for GPU. Okay, so computation requirement has increased, and AI also has increased it. Okay, increased our computation requirements. So we need more chips for processing information, and in parallelly, so that the energy requirement also increasing day by day. More transistor, so better efficiency, cost, energy cost for computing is rising. Okay, traditional computing system erase data, which leads to irreversible energy loss. This result in thermodynamic bottleneck and a need for massive cooling infrastructure. Even the quantum computer, so as discussed earlier, quantum computing gates are reversible, but the measurement is irreversible. Okay, but to keep away from the external influences, we need dilution refrigerators for quantum computers. Okay, that also takes energy. Okay, so the classical reversible computer, that is a complete alternative for the existing irreversible computer. But quantum is not for general purpose. Quantum is for whatever application which we are not able to do previously, we are able to do with superposition and entanglement. Okay, so we are having the higher parallel advantage of quantum computer. So here the energy loss is more compared to reversible computer, but even though this is different from the classical reversible computer. Classical reversible computer is an alternative to the existing computer, but quantum is not an alternative to the existing computer and applications. Quantum is for different purpose. Classical reversible computer can be In future, it can be the alternative for the existing irreversible computer. Okay, like general purpose computer. But quantum is not a general purpose computer. So quantum is designed for special task. So that power dissipation, cooling things, we should not confuse with it. Okay. So reversible computing, so decomputing, that is called decomputing. Okay. So you can compute and you can come in the reverse path. That is called decomputing. Okay. Allow energy to be recovered by reversing logic operation. Uses technique like adiabatic switching, resonant oscillator. So there are a lot of techniques. Still, it is in the research stage. Okay. So either you can double the computation for the same energy, or you can reduce the existing computation to half. So what is the future direction and challenges? So now transistor chip we have. In future, it may be silicon photonics is promising, but limiting in scalability and general purpose use. Quantum computers are logically reversible, but demand huge energy for refrigeration. May increase system level power by over a billionth time. Move to reversible classical chip. For general purpose, I am talking. Okay, for general purpose, classical reversible computing is good, but it's way ahead to go. So reduce cooling load, scale sustainable without higher energy, play a crucial role in future AI and HPC chips. Okay. Yeah. Okay. Any doubt? Just I'll just go through it. What is the purpose of using reversible in classical and reversible? Purpose is to reduce the energy. What is the purpose is classical? In classical to reduce the energy. When we delete while working on oh, that is okay. Shall we give loss of energy is independent of silicon type? Yeah, it is independent of no, but in general, information loss waste the energy. Okay, information loss is wasting the energy. Erasing the bit is wasting the energy. Okay, and dissipating heat. It may vary, depends on the material. Material to material, it may vary, but on the general, in general, loss will be there. That how much loss, that may be depend on the silicon type. What measurements are irreversible in quantum computing? Please give an example. Any measurement. So in Qiskit circuit, you are doing measurement. No, see, quantum state. For example, you are tossing a coin. So when the coin is in the air, it is in the both the state. Okay, head and tail. But when it fall down to the ground, that is a measurement. So it turns to any one state, either head or tail. That is a measurement operation. So in circuit also we are doing measurement operation. Okay, and that after measurement, that the answer is going to the classical. Okay, classical. Any measurement in quantum circuits, without measurement, you cannot collapse the state, and you cannot come to probability. No? But in quantum, it reversible. Yeah, gates are reversible, but measurement only irreversible. In quantum also, gates are reversible only. Course is not reflected in my. Okay, measurement Audio is not good. Hello, is it okay? Or? Okay, okay, thank you. Yeah, we'll go ahead. So reversible Boolean operations. Okay. So these are some of the, so like in classical irreversible computing, we have AND gate, OR gate, NOT gate. So here also we have a set of gates. Okay. NOT gate, Feynman gate, Fredkin gate, Toffoli gate, Firish gate. We will implement all these things and we will see. Flip a single bit. 0 become 1 and 1 becomes 0. Applying not twice returns to the original input. Okay. Basic reversible logic gate used for copying and controlling operation. This is nothing but C naught gate. Okay. Reversible Fedrin gate is nothing but C swap gate. Okay. Toffoli gate, Parish gate. We will see each and everything and their logics. So it's a end-to-end input to output mapping should be there. One-to-one mapping. Okay. Also, direct fan out is not allowed in the synthesis of reversible circuit because one to many concept is not reversible. But there is a concept called fan in, fan out. Fan in is okay, how many inputs it can have, and fan out is that circuit's output you can connect to other logic gates input. That is fan out. So that also, if you connect one output to two input, then that cannot be reversible. So always it should be one-to-one mapping. So direct fan out is not allowed in reversible computing. Okay, reversible circuit. Okay. Fan out is but required. Fan out because you have to give the output to other input. Na? So one gate output you have to give to other gates input. So it's achieved by using additional gates in reversible circuits. Okay, direct fan out is not allowed. Okay. So these are the number of parameters. So number of parameters that determine complexity and performance of the circuit. So number of reversible gates used in the circuit and constant number of inputs. How many inputs you are having and garbage output. For example, you have two input and two output. So one output will be interest of you and another output we are having just for the sake of reversibility. That output may not be used in our circuit at all. That is called garbage output. But we should have two input means we should have two output. Three input means we should have three output. So a dummy output also we should have for the sake of reversibility. Okay, that is called garbage output. And then quantum cost. This refers to the cost of the circuit in terms of primitive gates. That means basic gates are there. With that basic gates only we will implement the complex gates. Okay. So how many basic gates you are using? It is calculated knowing the number of primitive reversible logic gates you are using. So for example, you want to implement some gate. Okay. That gate can be decomposed into some three primitive gates. That means then the quantum cost is 3. Okay. So these are all the parameters to determine the complexity and performance of the circuit. Number of reversible gates, N, constant number of inputs, Ci, garbage output, quantum cost. So this is fan in and fan out. Fan in of a gate is the number of input that can practically be supported without degrading input voltage level specification of for a gate. For example, some gate, okay, it has some limit. That gate can take this much voltage only. Beyond that, if you give more voltage, that gate will damage. So that you cannot connect many inputs to the gate. Each input adds some voltage. Okay, for example, if the gate is capable of holding only 10 volt, okay, one input is 5 volt, then maximum you can give two input only. If you give third input, that gate will fail. Okay, so then fan in of a gate is a number of input that can practically be supported without degrading input voltage level specification for gate. Each gate will have some specification. For example, this gate may have 10 volt maximum capacity, this volt may can have 20 volt. So if it is 5 voltage input, then you can connect up to 4. So fifth you cannot connect. Okay. So this is fan in concept. Fan out is the number of output signal a gate can have without degrading its output voltage level. Okay, so output voltage, if you take multiple output, voltage level will decrease, so it will not reach the next input. So number of output also determines that output voltage will determine the fan out also. But in quantum, fan out is not allowed. Direct fan out is not allowed in quantum or reversible logic. Okay, so these are some of the metrics for reversible logic gates. The gate type is whether it is one input one output, two input two output, or three input three output. Okay, number of input and number of output. Quantum cost, number of quantum primitive gates required to implement it. Fan out indicates the direct fan out is not allowed. Duplication needs special handling. Okay, so you need the fan out operation, but you cannot do directly. So through different operation, you have to do fan out. Okay, garbage output. Just for the sake of reversibility, we need garbage output. Number of outputs not used in further computation. Gate delay, time to execute based on the basic logic, basic gate operations. Okay, so how much delay, so that you cannot build a big long sequence of gates, so that gate delay will increase. You can correlate with coherence time and other things, but gate delay, basically it is gate delay. Okay, primitive quantum gates, c naught, not, hadamard, toffoli, these are all the building blocks. Okay, and v dagger gates also there, we will explain in later. So v is nothing but square root of the Pauli X gate. If you put 2 square root of X gate, then it become X gate. It's a half X gate actually, you can call. Hermitius conjugate, that is inverse of the square root of Pauli X gate, is v dagger. Okay, so okay, what is Clifford gate and non-Clifford gate? So Clifford gate is a quantum gate that maps Pauli operations to Pauli operations under conjunction. Okay. So after interaction, the output also Pauli operation. Then it is called Clifford gate. If the output is not Pauli, non-Pauli operation, then it becomes non-Clifford gate. Okay. Clifford gate is a quantum gate that maps Pauli operation to Pauli operation under conjugation. A non-Clifford gate is a gate that does not preserve the Pauli group under conjugation. Okay. Clifford gates are easy and classically simulatable. Non-Clifford gates are hard, quantum power enabling, and require for universe. So these are all the Clifford gates. Pauli X gate, Pauli Y gate, Z gate, Hadamard gate, S gate, S dagger gate, C naught, control Z gate, swap gate, control S gate, control Z gate. Okay. And non-Clifford gates are T dagger, V dagger, Toffoli, CC is that control Z, rotation gate, this 90 degree, these things are Clifford gate only, but arbitrary angle, for example 0, so pi by 2, pi by 4 are Clifford gate. But rotation gate, for example pi by 3 or some in between, for example 0 to 45, if it is something different between this divisible by pi, then those are called actually non-Clifford gate. For example, if the angle is 23, then it is non-Clifford gate. Okay, universal gate, HT, naught. So these are some of the universal gate. Like in classical also we have universal gate, NAND gate, NOR gate. Okay. Similarly here also we have. This is just a classification. So if the input is Pauli and output is also Pauli operation, then it is called Clifford gate. Okay, if the input is Pauli and if it output become non-Pauli group, then it is non-Clifford gate. Okay. This is just a categorization. Okay. Okay. Any doubt? If a system is linear, it is reversible. Linear, non-linear, we cannot say. Yeah, we can. The number of input and number of output is same, then it is reversible. How does reversible work and reduces the energy? See, in reversible there is no erasure of information. Okay, so basically when you are erasing some information, you are losing energy as heat. Okay, so since in reversible there is no need for erasing anything. Okay, so the number of input and number of output is same, and they will loop the, there is no grounding operation here. Okay, qubit voltage level, I don't know exactly, but because that depends on how you are making qubit. You can make qubit with superconductor, you can make with photonics. Qubit is a generic term. You can prepare qubit with n number of methods: trapped ion, superconducting qubit. So each superconducting qubits they use uh, that is called that one. Yeah, so they use some, yeah, I will discuss that. So it depends on the material. So voltage, we cannot tell what is the exact voltage for qubit. That depends on the technology. Okay, so we'll take 5 minutes break. Yeah, yeah. So now it is storing information also need energy, right? How only erasing takes out energy? Yeah, storing. See, storing, you are storing first time, you are storing is just you are consuming energy but not wasting energy. Erasing is just that operation is gone. Information storing also need energy. Yeah, storing is nothing but you are erasing. See, if zero is there, you are storing one, means the previous is erased na? We have limited memory only. You can reset all the memory to zero. Okay, there is a command in Linux, dd command, if equal to 0, of equal to 0. That means you are filling the entire disk with zero. Zero also it's information. So you are not, you are erasing. So see, devices with the information only. New device also will be with information only. That is zero. You are converting 0 to 1 and you are interpreting as information. So information storing also, by storing only you are erasing actually. Whatever existing that location, something is there, 0 or 1 is there in the flip flop. It cannot be empty. Flip flop cannot be empty. It either it points to 0 or it points to 1. So by storing only you are erasing. First you are erasing, then only you are storing. Storing and erasing is same operation actually. After measurement, if answer is classical only, then what is the advantage of the quantum? Speed up or anything else? After measurement, if answer is classical only, what is the advantage of quantum? Yeah, speed up is a measure. Yeah. Okay, we will have break for 5 minutes. Yeah. 3-5 will start.